Hot wire anemometry is an experimental technique used for the measurement of velocity in turbulent flows. This technique relies on the variation in heat transfer from a small heated sensor exposed to the flow. In this case, the sensor is a small tungsten wire with a diameter of 5 microns and a length of 1.25 millimeters. These sensors are usually manufactured with materials whose electric resistance changes significantly with temperature, such as tungsten or platinum, since this phenomenon will allow us to generate a measurable signal. One of the main advantages of this technique is that, due to the very small thermal inertia of the wire, it is capable of detecting velocity fluctuations with a large dynamic response. For instance, the frequency response of this particular sensor is around 400 kHz. In our case, due to the electric circuitry available, we employ the hot wire in the so-called constant temperature operating mode. For this configuration, the probe is connected to an electronic circuit whose most important elements are a Wheatstone bridge and a feedback amplifier. Sensor and circuitry are connected through a low-noise coaxial cable. When a change in the flow velocity occurs, this system automatically compensates the change in the temperature of the wire, or in other words, its resistance, by changing the input of the input current intensity. Now, how do we calibrate this hot wire system? The system allows us to link the flow speed and the output voltage, but of course we need to calibrate it against a reference velocity sensor, which is usually a pitot tube. To this aim, during the calibration, the hot wire probe and the pitot tube are placed at the same stringwise location within the tunnel, and we can assign the output voltage given by the hot wire system to the velocity value measured by the pitot tube. These two quantities are usually related with a fourth-order polynomial. Note that the hot wire probe only measures the magnitude of the velocity vector normal to the wire axis. This means that a single wire probe cannot distinguish between different velocity components. To do so, we have to employ a so-called cross-wire probe that contains two or more wires at an angle. To calibrate this kind of sensors, we have to repeat the voltage-velocity characterization for different gyro angles. So the procedure becomes time-consuming and tedious. So trailing edge noise can be predicted on the basis of kinematic quantities measured close to the trailing edge. To predict noise employing hot wire data, we need to use first a Mietz model that relates the acoustic scattering at a sharp edge to the wall pressure field measured close by. And then we also need to use the so-called TNO Blake model that links the pressure and velocity fluctuations within a boundary layer by solving the Poisson equation. As you can see in these equations, the scattered noise is a function of the mean wall parallel velocity profile, the root mean square, and the power spectra of the wall normal velocity fluctuations. As explained before, to measure these quantities, we must employ a cross wire. To make things even worse, these models also require as input the correlation length of the wall normal velocity fluctuations in the wall normal direction. And to compute this quantity, we must acquire synchronous data with two cross wires, keeping one at a fixed position and then traveling the other probe along the vertical line. As you can imagine, this implies calibrating two cross wires, so the process is extremely long and tedious. And for this reason, other experimental techniques such as time-resolved PIV or wall pressure measurements are preferred. So this has been everything for today. If you need additional information, you can check out these references. Goodbye.